Today we will talk about the length of a curve and line integral. If there is a C1 curve, then we can calculate the length of the curve using this formula. Okay, so let's think about the circle of radius 2. For simplicity, we think about the circle centered at the origin. Then our circle will be like this, and let's say this is 2. So we draw the circle of a radius 2, and to find the length of a curve, we want to parameterize this circle. So let's say that the circle C of t is given by cosine t, 2 cosine t and 2 sine t. And our t will be 0 from 0 to 2 pi. Okay. It'll be better to like this. And it is a closed curve. And C prime t is given by minus 2 sine t, comma 2 cosine t. So if we find the norm of C prime t, then it is root of minus 2 sine t squared plus 2 cosine t squared. So it is given by 4 times sine squared t plus 4 times cosine squared t. And since sine squared plus cosine squared is equal to 1, so we can say that it is just the square root 4. So it is the same as just the 2. Okay. So we want to use this formula. So let's say our interval of a t is given by from 0 to 2 pi, and we found the norm of C prime t, it was 2, so we can calculate it to t from 0 to 2 pi, so it'll be 2 times 2 pi, so it is 4 pi. Okay, so we can say that the length of a circle is 4 pi. Actually, you can check that if the radius of a circle is r, then we know the circumstance of the circle is given by 2 pi r. So in this case, radius is 2, so we know that when r equals to 2, the length of the circle is 2 pi times 2, so 4 pi. So you can see that our result is the same as what we know before. Okay, so we can calculate the length of the curve like this method. From now, we want to find the line integral. It means that there is a C1 curve like this. And we want to integrate the function on the given curve. So if our curve is given, we want to integrate the function f on this curve C. So we can calculate it using this formula. And this a and b are from the interval of t, and we can calculate it using the f of c of t times norm of c prime t. Okay. So let's apply this method here. We want to calculate this integration, and let's say that f x comma y comma z is given by x plus y plus z. This is the integrand of our given function, given integration, and our c of t is given by cosine t sine t t. So c of t is given by cosine t sine t We want to use this method, so let's calculate the integrand first. Okay, to do this, f of c of t is f of cosine t sine t t. As you know, this is the x, y, z, so we just plug in x, y, z with respect to the terms in t. So x is cosine t, y is sine t, and z is t. Okay, and we can calculate the c prime t. So c prime t is given by minus sine t, cosine t, and 1 here. So we need to calculate the norm of the c prime t. Let's calculate it here. C prime t norm is square root of negative sine t squared plus cosine square t plus 1. So it is 1 plus 1, so equal to 2. Here, sine square t plus cosine square t is 1, so it is 1 plus 1. Oh, sorry, it'll be square root of 2. So by our formula, we can say that CFDS is calculated using the formulas from 0 to 3 pi. F of C of t, f of C of t here, cosine t plus sine t plus t. And our C prime t is with 2. So it is with 2 minus sine t plus cosine t plus 1 over 2 t squared. 0 to 3 pi. So with 2 times, minus sine 3 pi is 0, and sine 0 is also 0. Cosine 3 pi, cosine 3 pi, just a minute. Cosine 3 pi is equal to pi, and it'll be minus 1, right? Okay, so cosine 3 pi minus cosine 0 plus 2 3 pi squared minus those 2 times minus 1 minus 1 plus 9 pi squared over 2 minus 0. So it'll be 2 root 2 plus 9 root 2 over 2 pi squared. Yes. And we wanna calculate the line integral of a vector field. Actually, here we calculate the integration of the scalar function, but now we want to calculate the integral of a vector field. So it looks like the similar formula as before, but the different thing is we use here dot product, okay? Because this one and this one is this one and this one are vectors, so we cannot multiply it, so we need to use dot product here. Okay, so let's calculate it. First of all, we want to calculate the integrand. So our c over t is given by t plus 1 e to the t squared, like this. And we want to find first f of c of t. Then since f is this one, we can plug in x is t plus 1, x is t plus 1, y is e to the t, z is t squared. So z is t squared and y squared e to the t squared, and x is t plus 1. Okay, and our c prime t is given by 1 e to the t to t. So let's calculate it. Interval is 0 to 2, and f of c of t is given by t squared e to the 2t t plus 1, right? And we want to calculate the dot product with c prime t dt. So it is from 0 to 2, dot product t squared plus e to the 2t times et plus t plus 1 times 2t. Okay, t squared times 1, and then e to the 2t times et, and t plus 1 times 2t. I calculate the dot product here, and we want to integrate this function. Let's simplify it first. So t squared plus e to the 3t plus 2t plus t squared plus 2t. And it is from 0 to 2, e to the 3t plus 3 times t squared plus 2t dt. Then it is e to the 3t times 1 over 3 plus t cubed plus t squared. So from 0 to 2, we get 1 over 3 times e to the 3 times 2 minus e to the 0 plus 2 cubed minus 0 plus 2 squared minus 0. So it is 1 over 3 times e to the 6 and minus 1 over 3 plus 8 plus 4. So it is 1 over 3 times e to the 6 plus it is 12. So 35 over 3. We got the result like this. And we can see that this integration of the vector field is given by this formula. And we know that this dot product can be written as f of c of t. This is the norm times norm of c prime t times cosine theta. And here theta is the angle between f and c prime. Okay, so our at each point, this integrand, the sign of this integrand depends on the angle, because this one and this one are positive, but this one can be negative, depends on the angle theta here. So let's think about this first one case. I draw the line here. We want to integrate the vector field along this curve, actually this line. And this black arrow represents the vector f, and this red line is our c of t. And you can see that at each point, f and our tangent vector has the acute angle, so cosine must be positive, right? Cosine must be positive. So you can say that along this curve, integrand is positive, so this integration must be positive. Okay. Um, okay, for this one, we check the angle, right? The vector f and c prime means the tangent vector. So when we think c of t here, then c prime t is given by like this. It depends on the direction of the c of t, so you need to check the direction of the curve. So if we say the curve is given by like this, the curve is this direction, then we can say that the tangent vector at this point is given by like this. Okay, so in our first figure, if we fix one point here, then you can see that the curve goes to like this. So tangent vector at this point is just the given by like this. This is tangent vector c prime t, and which color is better? I'm not sure. Purple. That's purple. So f is given by like this. Okay, this is f, and this was c prime t, and as you can see here, this angle must be acute angle. So this angle is less than or equal to pi over 2, so our cosine theta must be positive. So it means that our integrand f in a dot product with c prime t is bigger than 0. At its point, this integrand is positive, so we can say that the integration of f, the product, s must be positive. Okay, we can say that like this. Let's think about the second case. In this second case, let's think about the tangent vector first. Let's see here. Tangent vector is given by like this. This is a c prime t or c prime t, and you can see that the f is this direction, right? So our angle must be this one. Okay. So this angle is also acute angle. And so you can say that the our integrand f the product c prime t is greater than or equal to 0. So and as you can see at each point the angle must be acute angle. So along the curve our integrand are positive, so we can say that our integration must be positive. Okay, we can think about it like this. Okay. If the curve is piecewise the C1, like this is there are 3 C1 curves, then we can calculate it along each C1 curves, and we just add them together. Okay. For example, let's say that the C, our curve C, is a triangle. Joining 3 points. Let's say it's x, y, z axis, and here 1, 0, 0, 0, 1, 0, and 0, 0, 1. And our C is given by like this. There are 3 piecewise curves. Just a minute. Okay. it is given by like this. So we want to calculate it. Sorry, I mistake the direction of the curve. Okay, cool. Let's say this is C1, this is C2, and this is C3. Okay. For C1, the curve from 1, 0, 0 to 0, 1, 0, we need to find the parameterization of the curve. Actually, if we know the 2 points, then we can find the parameterization of a line by using 1 point and 1 direction vector. So the direction vector is given by the subtraction of 2 given points. So we can say that minus 1, 1, 0 is the direction vector. Direction vector means this direction. It will represent this direction. And so if we set as C1t is our first point, 1, 0, 0 plus TV, V is minus 1, 0. So it'll be given by 1 minus t, 1, 0. Then you can check that C1 of 0 is given by 1, 1, 0. Why it is 1 on, sorry, I have a mistake here. Here must be t, so the second coordinate is 0. So it is our first given point, start point, and C1, 1 is given by 1 minus 1, 1, 0, so 0, 1, 0, our end point, okay? C1, 0 is our start point, and C1, 1 is our end point, and it is the linear line. So we can parameterize the C1t like this method. And, to calculate the C1 f ds, we can calculate it like C1 f of C1 of t dot product C1 prime t dt. Okay. Here it is better to use the inverse a from a to b, but here a is 0 and 1 is b is 1 because 0 comes from our start point and 1 comes from our end point here. Okay. And let's calculate it. Our f is given by like this, and our C1t is this one. And let's compute f of C1t, then we get e to the z is 0, and e to the y is t, and x plus y times C1 prime t. Our C1 is this one, and if we take a derivative here, then we get minus 1, 1, 0, and it is actually the vector v. So we can say that it is minus 1, 1, 0 dt. Let's simplify it first. E to the 0 is 1, and e to the t, and it is just the 1. The product with minus 1, 1, 0 dt. We integrated from 0 to 1. So it is from 0 to 1. If we take the dot products, then it'll be minus 1 plus e to the t dt. So it is negative t plus e to the t from 0 to 1. So you get negative 1 plus e to the 1 minus e to the 0. So minus 2 plus e. Okay. So you get this one. Actually, we just calculate the integration on the line C1. And so to solve this problem, you need to calculate it along the curve C2 and C3 and add them together. Okay, so I will just let the left things. Okay, the rest things are just the exercise. So I put the, integral C2 f ds is 3 over 2 minus e, and C3 f ds will be negative 3 over 2 plus e. So this one, this one, this one added together. Then our C of f of ds would be given by these three things: sigma from I to 3, Ci fds. So along C1 curve, we get minus 2 plus e. Along the second curve, 3 over 2 minus e plus minus 3 over 2 plus e. So e minus 2 is the answer. So I skipped the calculation here, but you can check it. You can check it, okay? Okay. Let's record that the gradient vector field is the gradient of some function. So we call this function f a potential function, okay? And when we integrate the vector field, here gradient field, then as a fundamental theorem of calculus, we can calculate it using the end point and the start point of the curve. One thing, very important thing is, if C is closed curve, then this integration must be 0, because closed curve means C of A and C of B are the same thing. So these values are the same, so it'll be 0. And also it is very important. I mean, this C, in general case, if we take a line integral, then this C, this integration depends on the choice of the curve C. But if f is a gradient field like this, then it only depends on the end points. So it does not depend on the choice of a curve. So we can choose a curve to simplify the calculation. We do not need to take a very complicated curves. We can choose very simple curve because it only depends on the endpoints. It means that if this is curves CAB, we do not need to calculate the gradient f. I mean, we do not need to calculate the integration along these very complicated curve. We just use, this line. Or if it is more great, then we can say like this curve. Okay. It depends on the problem. We can choose the simple curve. Let f x, y, z given by xy times sine yz, and our vector field f is just the gradient f. That means that f is the gradient vector field, So this integration C of f the r is only depending on the endpoint here. So if we think about this one, actually we do not need to find the parameterization of C, okay? Because we know that start point is this one and end point is this one. So we only need to do is, C of f dot dr is same as integration C gradient f dr. So by the fundamental derivative calculus, it is C of B minus f of C of A, and our endpoint is given by 1 pi, and our start point was 0, 0, 0. So we only need to calculate the value of this function. So f is this one, so we can calculate it. 1 times sine pi minus 0. So sine pi is 0, so it'll be 0. Okay, it's very simple, right? But if you don't know that the f is gradient f, then you need to set a line C of t first, and then you can calculate it. But in this case, it's a gradient vector field, so we can take any path, and also it only depends on the endpoint. So actually, we do not set a specific path. Okay, without the path, we can calculate the integration here. It's very useful. This is the last problem. And let's say to find the potential function for f and evaluate the line integral of f over the given path. Okay, what I want to do is we want to find the f satisfying this one. Okay, so I think it's better to write out like this. 3, 6y. Okay. You know, gradient f is given by f x and fy. Okay. So we have equation like f sub x is 3 and f sub y is 6y. And from the first equation, if you integrate with respect to x, then you get f of x comma y as given by 3x plus some function of y. Maybe it is better to write out the more detail. Here, fx equal to 3 means df dx equals 3. Okay. So if we integrate both sides with respect to x, then it'll be f of x comma y and 3x plus, we use this constant here, but in this case, you know, df, when you say df dx, let's think about the fxy, and when you calculate df dx, we think y as a constant, right? For example, let's say that fx comma y is xy plus x, then we calculated the f dx like we assume that y is a constant, so it is just the 3 times x like that. So it'll be just the y plus 1. We can differentiate like this, you know, we just think y as a constant. Okay, it's not a variable when you think about the partial derivative with respect to x. So when I find f from the partial derivative, then here is not just the constant, because we thought that y as a constant, you know, so when you recover f of x comma y, there must be the term of y. okay? So since there will be a y, term of y, so I just say that it is the term of the y. It can be a function of y. So I just said it like this. And to find the h of y, we use the second equation. So it means that from this one, we will differentiate the this fxy with respect to y. Take a partial derivative. Okay. Then in the case we think x as a constant because we take a partial derivative with respect to y. So it'll be 0. And we can say that it is h prime y. Okay. And from the second equation here, we know that fy must be 6y. Okay. Then from this, you get h prime y is equal to 6y. So it is hy is equal to y squared, 3 times y squared plus some constant. Okay. Here is not a function of x because you know this h is only the function of y, so we do not need to say that it is the function of x. Actually, in this case, it was the function of x and y. We had to find two variables, so there must be the term of the y here. But in this case, we just said this term is just for the terms with respect to the variable y. So when we recover h of y here, it is just the real constant. Okay, so we can say that f of x comma y is given by from here 3x plus hy we found it here 3y squared plus c. Okay, so let's say that let's check is really potential function for f. Let's compute the gradient f here. Then you get if it is fx and fy, so you can calculate it 3 and 6y. Okay, you can see that it is the potential function. F is the potential function for f, vector field f. And c does not depend on the our result, so we just put c equal to 0 here. Okay, so let's say f of x comma y is just the 3x plus 3y squared. So in this case, we want to evaluate the line integral of f along the path. Since it is just the gradient f, the s by the fundamental theorem of calculus, it is r of the first point and the end point, r of the first point. So you put t equal to 4 here, then you get the end point t comma 2 times 1 over 4 here minus f of the start point is 1 comma 2 here. So if we put them, why it is the 1? It is not 1. We can put t equal to 4 here, so it must be 4. Okay, so it is 4 comma 1 over 2, so you can plug into the f here. F is not that one. This one is f, so you can plug in. I think it is better to simplify it first. So f of 4 comma 1 over 2 minus f of 1 comma 2, and for this f, we can say that 3x, 3 times x plus 3 times y squared minus 3 times 1 minus 3 times 2 squared. So it'll be the same thing, and to say that 3 over 4 minus 3. So it'll be negative 9. Is it right? Okay. Yes, we can calculate it like this. Yes. I will stop here.